Hello, and welcome to a brief demonstration of Dynamic Designer for Solid Edge. Over the next 6 minutes, we'll show how to take a solid edge assembly design and create a functioning dynamic model of a jack mechanism, where we can analyze forces and input requirements. There are two main objectives for this demonstration. The first, to determine the input torque to raise a given load, in other words, the mechanical advantage of the system. Second, we'll determine the loads acting on a specific component and transfer those loads to an existing solid edge simulation study. Let's get started. We'll start Dynamic Designer by selecting the motion icon under the Environs ribbon. This will activate the Dynamic Designer browser. Alternatively, in building our motion model, we can also use the features in the ribbon bar. Let's go ahead and begin by defining the moving, grounded, and attached parts for the mechanism. We'll select the base, the two base pins, and the bottom coupler and define them as grounded parts. Then, we'll use the lift pad, the two lower arms, the guide nut and screw nut, the screw, and the upper arms, and we'll define those as moving parts. Notice the message that appeared. Also notice the icons in the graphics area. Dynamic Designer automatically assessed the solid edge assembly relationships and converted those into equivalent motion joints. This means that any change done to the assembly relationship will automatically update the motion joint in Dynamic Designer. Let's go ahead and continue with the remaining parts. We'll select the bearing and the bearing cover, and we'll rigidly attach those to the guide nut. The top coupler and the two top pins will be rigidly attached to the lift pad. And then finally, the crank tab and the sleeve will be rigidly attached to the screw. Next, we'll run a simulation by selecting the simulation icon to allow gravity to act on the mechanism. We can click, hold, and drag the playback slider to review the results. Now you can see we are still lacking some of the important constraints, which we'll now go ahead and add. We'll select the simulation button again to delete the results and allow us to be back in edit mode for the model. There are 4 features we still need to define to complete the motion model. The first, a screw joint. Second, a contact or collision between the ratcheting gear teeth. Third, a motion on the screw. And fourth, a force acting on the top. To add the screw joint, we'll first remove the standard joint that was created from the assembly relationship. Next, we'll use Dynamic Designer to add a screw joint between the screw and the screw nut. We'll give it a location and a direction. We'll leave the default screw pitch at 0.2 inches per revolution. Next, we'll define the contacting gear teeth pair between the upper arms and the lower arms. Next, the lower arms. Then we'll add a motion to rotate the screw. We can locate the joint that attaches the screw to the guide nut, and we can apply a motion directly on the joint. We'll assign 720 degrees per second or 2 revolutions per second, and negative will reverse our direction so the jack is moving upward. Lastly, we'll define a force acting on top of the lift pad. Now we're ready to run our simulation. We'll go into our simulation parameters and we'll set the duration of the simulation and the number of frames. Now we'll select the Simulate button to run the simulation. The simulation took approximately 30 seconds to complete. We can now click, hold, and drag the playback slider to review the final results. Now the first objective of the simulation was to determine the amount of torque required to turn this screw and raise the load. We can plot the torque requirement necessary to do that. The second objective was to determine the loads acting on this arm and then transfer those loads to a solid edge simulation study. We can start by adding resultant force graphics. These help us visualize the directions of the loads. We can see the red forces, which are the normal force reactions, and we can see the yellow moments. We can also plot in graphical form each one of these features. Here we can determine which load case might be the worst condition we wish to analyze in FEA. Once we find that load case condition, we can simply right-click on the upper arm name under the Solid Edge Simulation node and add loads. This has automatically added the loads onto that part for our Solid Edge simulation. If we close Motion and we enter Solid Edge Simulation, we can see all the loads that were applied automatically to this part. This completes this demonstration of Dynamic Designer.